other example. For example, we know that in classical statistical mechanics, we know that we have probability distribution at different time and different temperature. We know that also probability distribution describes, for example, now we have here some fly or whatever, which moves in this room where we are sitting. And this fly is attacked by molecules and small particles. Because at the time temperature, any fly or whatever is attacked by environment. And at the given temperature T large, then the small particle has no exact position momentum. They fluctuate. And this fluctuation is associated with probability distribution of position momentum at given temperature. And this is very well-known formula for which describes this probability distribution. So lesson, in classical mechanics, both mechanics and statistical mechanics, the state of a particle is associated or described by probability distribution of two random variables, position and momentum, which varies in the time or varies or depends also on temperature. But then, this is our lesson. Then what we know else about this? Something new we learned right recently, I will show you now, even in classical statistical mechanics. It has not been considered here. Why? Because in the beginning of last century, Radon, mathematician, discovered what is called Radon transform. We know that physics is based on Fourier transform. All what we know, frequencies, time, and so on, it is Fourier transform dependent knowledge. And all our science is based on Fourier formulas. But it was several centuries ago, not very much, nevertheless. Nevertheless, last century, a mathematician Radon discovered that there exists transform which provides possibility, for example, having a probability distribution describing classical particle trajectory, f of qpt is shown here by function f, and taking integral with delta function, which is written here, where x is specific position, I will tell you later what it means, minus coefficient mu and coefficient nu times position and momentum, and integral, provides a function which is called Radon transform of standard probability distribution, describing classical particle and its trajectory depending on time. Because the distribution, which is called tomographic, I will tell you why tomographic, probability distribution, gives possibility to reconstruct initial probability distribution. So it is map of initial probability distribution of classical statistical mechanics or classical distribution function, f of qpt, of two random position and momentum depending on time, with another probability distribution, which is called tomographic probability distribution, where what is x? X, it is position in specific reference frame of classical particle. I will show you later a little bit after this. Why it is important? Because we are able, in classical statistical mechanics, to map one very well-known probability distribution of position momentum onto another probability distribution, which is denoted as conditional. Condition means, you see here a line, which shows that in condition at time moment t and with extra parameter mu nu, which describe, I will show how, a reference frame where position is measured and random variables is position. There is this map of one probability distribution onto another probability distribution. So two classical probability distributions are related. The point is that due to Radon, by the way, he discovered his formula, which I show you next one. in the beginning of last century, during First World War. Nobody worried about this. Nobody wanted to know what means radon transform. Now, after 100 years, it's important to understand better what it means radon transform. Radon transform showed that if we take Fourier transform of the what is called condition probability distribution, depending on position x, large x, what is the position, measured in specific reference frame, taken in phase space of classical function of classical particle. Then you see there is one probability distribution is mapped onto another probability distribution. Why I'm showing this? Because if we apply the same formula for classical statistical mechanics of the particles having been among the other particle at temperature T, we know that standard, what we very much accustomed, probability distribution can be, and it is probability distribution of this temperature. If temperature is going to 0, the particle is temperature T is described by delta function Q, delta function P at the temperature T, because this function, which we know in classical statistical mechanics, goes to 0, goes to delta product of delta functions. So in classical statistical mechanics, we can associate state both is fixed temperature equal to 0, or if there is no fluctuation of position momentum, and at the temperature where there are fluctuation, with some probability distribution, which is shown here, which has standard understanding delta of Q, delta of P, if the particle is without interaction with any environment, and with trajectory, which in the temperature T, which is shown here, it is also described by function which is probability distribution. Intuitively, it is clear in probability distribution. Now I go to quantum mechanics. What is going on in quantum mechanics? 100 years ago, Schrödinger discovered that state is described by complex wave function. What is wave function? It is not clear intuitively, classically, it is not clear even now. Complex function has modulus and phase exponent of this kind. Also, this Landau in 1927, after Schrödinger wave function, discovered that another representation of state, which is used for temperature, like a classical statistics, can be used. It is so-called density matrix. Density matrix is complex function in position representation. Why it is matrix? Because x and x prime, it is like Coulomb and row in matrix. Due to this, is called density matrix. So wave function, intuitively unclear classically, and density matrix, intuitively unclear classically, what they mean. Nevertheless, quantum mechanics, 100 years, is based on notion of state of a system, of a particle, or of all the other systems, like this function, like these two functions, wave function and density matrix. Now, the question is, what we can understand as we understood in classical mechanics? We know that modulus squared of wave function is probability density only of position, but it is not the state. It is not enough if you know only this probability to say that you know the state. Also, if you know diagonal elements of density matrix, which is also probability density of position only, but also it is not enough. We have to know all the coulombs and all the row ingredients of density matrix. So function of two variables. But this distribution do not determine the quantum states. Then the question is it possible or not, nevertheless, to find probability distribution standard, which is, we understand classically, which describes the quantum states. There was a dream, and this dream was almost 1 century, And only now, only this last decade, it was understood that it is possible to introduce probability representation or probability distribution which describes the quantum states like in classical mechanics. Exactly. It was very difficult, long way. And to do this, and now I will speak about mathematics of quantum mechanics, because in quantum mechanics, wave function and density matrix, or density matrix is operator, is density operators are used in quantum mechanics to describe the state in quantum mechanics, both even now in classical, in high school, but especially in university, all these lectures on quantum mechanics. Question: in order to introduce what I did tell, what was found recently, I will tell you what means another aspects of quantum mechanics from the point of view of mathematical apparatus. Let us consider Hilbert space. Hilbert space where live state vector, it was Dirac who introduced Hilbert space vector, which associated or described the wave function. And density operators are operators acting in Hilbert space, on Hilbert space vectors. So it is standard notation in quantum mechanics, and let us suppose, and it was a result of last 10 years only. And there are references which are shown here where this has been introduced with Olga Manko, Giuseppe Marmo, and myself, and this is written here, the references. And let us suppose that we are lucky to find two families of operators. U operator called dequantizer, and D of the same operator acting in Hilbert space, and parameters which define these operators, because it's a function, some vector x, which can be multidimensional, x1, x2, xn. And these parameters can be both discrete or can be continuous or mixed. Discrete and continuous. Let us suppose that we are lucky to find in mathematics new formula like Radon did more than 150 years ago. Let us consider that, and I will tell you why quantizer and dequantizer. Quantizer is quantum mechanics. Quantum mechanics means that we have quantum objects. Quantum objects usually are operators: energy operator, momentum operator, position operator. But in classical mechanics, we very much accustomed to functions. So classical will be considered function of the vector x or classical parameters. Then the question is, if we have operator, but want to get function, because probability distribution is function, what we are doing? We call this, we dequantize. We map operator, density operator rho, onto function of classical variable x. Due to this, if this operator exists, we call this dequantizer. Dequantizer dequantizes all the operator, it maps onto function. But in order to have the same information which is considered in which is given by operators, we need to reconstruct back, because in quantum mechanics we have the state if we know density operator or wave function. But then we need inverse transform. So let us suppose that there is another operator, family of operator, D of x, which we call quantizer. And this quantizer makes BEP, density operator, onto this function f rho. F rho is also called symbol of the operator. So we have pairs, operator and its symbols, and the information in operator and its symbol is the same about the state rho. But then the question is, can be symbol density, can be symbol is probability distribution. As I did tell, 100 years, there was a dream to find the map of state expressed in terms of density operator onto probability distribution. It means that there was not known such quantizer and dequantizer which maps quantum states expressed in terms of density operator of wave function onto probability distribution without losing information about the states. But then it turned out that if the function symbol of operator rho is shown here, if we found correct, good dequantizer operator, if this function has properties of the probability, has probability of density operator, then it turns out that we can find such probability. But what are well-known properties of the density operator, which is well known in quantum mechanics, found by Landau? The property are the following one. Hermitian conjugate of dequantizer operator, which is shown as U dagger of x, is equals the same U of x. Also, trace of this operator, which in fact is probability distribution integral, known for usual probability for usual density, is equal to 1. And also, all the eigenvalues of this Hermitian operator are non-negative. Then the symbol of this operator, f rho of x, has exactly the properties of probability distribution. So if we are lucky to find quantizer and dequantizer pair, then we are lucky to find. What is, how to say, a mystery? In principle, this problematic of mapping density matter onto some function was very well known as idea to find something. But it turned out that Wigner in 1932, what I have written you about this quantizer dequantizer, nevertheless in complete sense, is found in these papers which I shown, which is done with my Italian colleagues. Then Wigner, famous American scientist, physicist, he was one of first dreamer to find probability distribution, but he found quantizer and dequantizer which provides probability, provides not probability, but function which is called Wigner function, which is similar to classical probability distribution which I described previously. And I now will show you what is this dequantizer. Dequantizer is written in Dirac notation, Dirac vector bra and ket, which is operator in bra and ket shown in such form as I written, and its Fourier transform written in such a form where dequantizer operator is shown by means of position x vector, which is eigenvector of vector q plus u over 2 is eigenvector of the position operator. And the same vector q minus u over 2 is eigenvector of position operator. Then the Wigner function, which is shown here using this dequantizer, is written in terms of wave function. It was possible to map wave function. It is not wave function itself. It is wave function corresponding to density operator. But if we know wave function, we know Wigner function. And it is very similar to probability distribution. But it turned out that this probability distribution can take of position momentum like in classical physics, but can take negative values. There was big discussion, is possible or not to have probability which is negative. Of course, it cannot, but Feynman, for example, was discussed. Many people were discussed. It turned out that Wigner function is not probability distribution. Nevertheless, it determines, you see, inverse transform, product of wave function is a matrix element of density operator and position representation is given by the integral. It is not Radon transform, but it is also similar to Radon transform because Fourier integral of Wigner function provides you density matrix and position representation. Then the question is how we were able to be lucky to find in quantum mechanics the quantizer and the quantizer. It turned out that it looks as follows. The quantizer operator is delta function of operator which is written here. X, which is position, unity operators minus parameter mu times position operator Q operator minus nu of P. So it's operator. But then the question is, what turned out with quantizer? And quantizer, if I will remind you now, what was for quantizer and the quantizer for classical mechanics. For classical mechanics, I will show you how they look. In classical mechanics, they look as follows. You see the radon trans, how it looks like. It looks as follows. It looks as integral of delta function with delta function analogous like shown here. So our quantizer, the quantizer, is expressed but not by the operators, but by the usual functions. By the integral are shown not by operators, but by the function. So if you know classical one, we in principle could guess the form of operators in quantum mechanics, but it turned out vice versa. First we found quantizer and the quantizer in quantum mechanics, and then we found how it turned out to be organized in classical mechanics. So after many centuries of Newton classical mechanics, it turned out that we can introduce the same notions of quantizer, analogous to, but classical-like, quantizer and the quantizer in quantum mechanics. Then, what is going on? It's going on that our probability distribution, which we introduced, called quantum tomographic probability distribution. Now I will tell you why it's what it means. So it is, the formula is the same like in classical mechanics, but here our probability distribution is trace of density operator with delta function of the quantizer. And inverse transform is exactly like in classical mechanics, but it is integral expressed by means of probability distribution for the operator, which is exponent, which is like Fourier transform. So the question is, why it is better? Because now, instead of wave function and density operator, we can use standard probability distribution of position measured in specific reference frame labeled by parameters mu and nu. Now I will tell you what it means. It means that in classical statistical mechanics, if you will consider this probability distribution, we know that probability distribution of position and momentum is called position momentum and reference frame with axis position and momentum. Because there are two axes perpendicular each to the other, we can rotate it and have a different scale. Instead of centimeters, to have meter and so on. And instead of time, have second and 1 hour or whatever. Due to this, our momentum can be measured in different scale. If we consider ensemble of reference frames where we are measuring the position, and all these reference frames are labeled by mu and nu, where mu and nu are function of rotation angle of this axis and scaling parameter. We change the scale of length and scale of time. Then we will get exactly position x measured in this reference frame. What it means? It means that in usual case, let us suppose that when we are measuring position, our axis, our time, or our velocities, or our momentum, and our position fluctuate, become random. So we are measuring position in random phase space. random phase space where all the axes are random, axes, position and momentum are random, and this randomness is described by rotation of this axis and change in scale. So mu and nu are these two parameters. Then we have this situation. Then the question is, but what if we will make not only for density operator, but for all other operators? Is it possible or not? The answer is yes, we can do it also for all the other operators, such map which is shown for the operator A, and then we have symbol of this operator A, which can be which is called here fa of y, and we can reconstruct this operator. But then the question is, for example, we considered not only density operators, but all the other operators. We can consider their symbols. They are not after this, they are not, if we are choosing this operator differently, they are not probability distribution. For only for density operators, they are probability distribution. But for this operator, nevertheless, it is important to know that we can consider all the mathematics of quantum mechanics with all the other operators by means of this quantizer and dequantizer, and it means by these symbols. But then the question is, can we consider relation of this symbol, different symbol, each with the other? And the question is, it is as if we have different reference frames, and reference frames are related with each of the other. And if we have two families of quantizer and dequantizer, one is d of x, and another is its quantizer, and d prime of y is different variable, x is different variable, and the same for u of x and u of y. So we have different kinds of symbols. The question is, there is the same information, and we can map one symbol on the other. And the result is the following one. The symbol of operator A of y variables is expressed by integral transform in terms of symbol of the same operator of x in terms of integral transform, where kernel of this integral transform is trace of dequantizer of y variables and quantizer multiplied by quantizer operator with x variables. So this expression provides the possibility to express probability distribution which we introduced in terms just now, tomographic probability distribution, which is random variable position and reference phrase measured in reference frames labeled by parameter mu and u, rotated on different scales, in terms of Wigner transform. So we did what Wigner dreamed. Wigner dreamed to find probability distribution, found Wigner function. And we found that this Wigner function contains the same information about state that our probability distribution, tomographic probability distribution. And inverse transform, if we know this probability distribution, we know Wigner function. It is given, again, you see the same transform which was given for standard classical mechanics. Similar, formula is similar, the same in quantum mechanics, for quantum mechanics Wigner function, and for quantum mechanics tomographic probability distribution is related, like in classical statistical mechanics, probability tomographic and probability in phase space are related, the same formulas. It's very strange, but nevertheless it is mystery. For me, it is still mystery. Now question. Скажите, пожалуйста, сколько времени я потратил? Не знаете? 30 минут. У меня 40. Хорошо. Now the question is, it's possible or not if we all the quantum mechanics express in this as it was given. So to map standard quantum mechanics from textbook to quantum mechanics where states are related to distribution. So I have written here Schrödinger equation for wave function with Hamiltonian of harmonic oscillator, and also Schrödinger equation for energy levels, which is written in the form of, which is very well known for oscillator energy level. The wave function is given by exponent Gaussian, and Hermite polynomial, which is well known. So this is a very well known formula. I only cite them. And then the question is, how looks what we know in terms of wave functions on the Hermite polynomial for the probability distribution? And it turned out that integral which I have shown can be taken, and in this probability distribution, the state with energy level is described by this. This is standard probability distribution. Everybody who has computer can see that this is positive probability distribution of position measured in reference frame labeled by parameters of reference axis mu and mu. But then the question is, we know that Wigner function can be expressed in terms of probability distribution. But then the question, if we know wave function, which every student in university all his life, first and second courses, is studying this probability, this wave function. Then, if we know wave function, how we know this probability distribution instead of wave function? And this is integral transform, which is very well written. It was found recently, formula, but nevertheless, you see, we can express, instead of wave function, we can find probability distribution. This formula just corresponds, in oscillator case, the upper formula. But then, for example, for Hamiltonian standard free particle, what we can know about wave function? We know very well that this free particle has integral of the motion, which are time dependent and linear in position momentum. This formula is like in classical mechanics. If you know classical position and momentum, we have this function without this notation, this operator, which are known as integral of the motion in classical mechanics. Now, this integral of the motion satisfies this condition, and if we have sums of integral of the motion, we have other integrals of motion which obey the relation A dagger is equal to 1, like standard creation and annihilation operator of oscillator. And then we know wave function of ground state of oscillator, and it is obeying to Schrödinger equation that I have shown, and it is known as wave function of this ground state of function moves as follows, as Gaussian. But then the question is, for example, we want coherent state to know. Coherent states, all the lasers use coherent states of photons, and photons behave as oscillator, and they behave as this coherent states in laser. And all our computers and other things use lasers, and this is what I'm speaking about, this laser, but in probability representation. Now it is free particle, and for free particle, coherent states is eigenstate of integral of the motion of oscillator like Hermite polynomials. And now I will show you how it can be found. Probability distribution which moves as coherent states in usual representation of wave function. For example, it is known that density operator of oscillator, if we know operator evolving as evolution operator, the exponent due to Schrödinger equation is exponent of minus IT and Hamiltonian. It means that density operator behaves as follows. It evolves due to given density operator at initial moment t equal to 0. Then, applying this operator's evolution operator, quantum one, we will get operator and time moment. Then this gives us possibility to find what is going on is evolving this probability distribution in quantum mechanics. In quantum mechanics, we have to use the quantizer, and we are writing formula, trace that our probability distribution, tomographic one, which we introduced, is equal to trace of density operator taken in time moment t with delta function of Dirac, which is our dequantizer. But then it is very interesting story in mathematics that if we use this formula and put density matrix in terms of delta function, we can use this U and U Dega operator and make them transposed. Transposed means translated. We can put operator U and T around density matrix rho at time moment t and put this U operator T on the right side. So our operator U and U of Dega make rho operator only at the time moment 0, but our U of T on the left and U Dega of T on the right, due to properties of this mathematics, can be put inside of delta function. And now position and momentum operators becoming Heisenberg position and momentum. But Heisenberg position and momentum operator behave as this function is written, also in terms of exponent of given evolution operator. And then it means that our operator QH of T becoming Q plus P of T, and PH of T equal P. So instead of parameters mu and nu, then we can introduce another parameter which provides the same previous function. So our mu QH of P minus nu PH of T becoming like it was before, but our mu and nu have to be replaced by mu H and QH, which gives this equality. But this mu H and QH are given in terms of interval of the motion, means that our mu and nu becomes nu plus mu q, like in integral of motion, and mu continues to be mu. You remember that P was P and Q was Q plus PT. So our mu and nu behave as usual position momentum. And we immediately get evolution solution of Schrödinger equation for harmonic oscillator with time dependence. And the same can be done for all other functions. For example, for coherent state, we have exactly the same trick. If we know this for standard coherent state without evolution, we have the same transposition. For the state of free particle, we have the same property. Also, the same probability distribution describes the energy level of harmonic oscillator, which is shown here as probability distribution described here. So it is very easy to do if you know this trick. But then the question is, as I mentioned, in optics, there is the same description. Photons is the same rotating oscillator beam, but we can do in optics only rotation without scale. And it is called optical tomography. And all the experimentalists in quantum mechanics in all the countries, even in Russia now, and also in Lebedev Institute, now can measure optical tomogram. Optical tomogram is a specific tomogram which I presented here. The only that mu and nu are equal cosine theta and sine theta, where we're using only random rotation of reference axis in phase space. And then we have the same story. Our mu and nu now are simpler, and now optical tomogram for free particle looks as follows, and our oscillator eigenfunction energy levels look as shown here in terms of for optical tomogram, which now measure oscillators, can measure oscillator state. Now, the last story which I will tell you a little bit how much I have. I have 5 minutes. Which, okay, but we started 5 minutes later, so I will use this 5 minutes. So the point is, we can do the same for qubits, for spin states. For qubits, we have wave functions which are shown in form of Dirac vector, which are shown here. It is wave function of spin 1/2 particle, where spin looks up for axis z, up for axis x, and up for axis y. This is wave function, and these are density matrices of such states. But then the question, given density matrix, how we will find after this probability distribution? Very simple. We have to map this density complex matrix onto probability distribution. On what probability distribution? It turned out it is called dichotomic. Yes and no. It is two-way. Yes and no. Up and down. This is P1, probability to look up along x-axis, and 1 minus P1 to look down. Also for axis y, up and down, and then for axis z, up and down. So 3 probability distributions. They satisfy inequality for which must satisfy every density matrix. So our complex density matrix mapped onto 3 probability distribution with known quantizer and dequantizer. So in terms of wave function, it is given like here. This is our wave function, and this is a probability distribution which must satisfy purity relation because it is pure state and purity parameter, which is trace of density density matrix square. But then the question is, how for qubits we can write Schrödinger equation? Very simple. For state for spin 1/2, our Hamiltonian is 2 by 2 density matrix. So the Schrödinger equation for energy level is written for vector, but any equation for 2-dimensional vector can be written in terms of 4-dimensional vector if our matrix is considered matrix energy, which is shown here instead of energy, but state vector is, but 4-dimensional vector, we simply consider matrix, which is given as 1, 2, 3, 4 matrix elements, and we put it as Coulomb, like here. So, because our probability distribution is written in terms only of probabilities, P1, P2, P3, like shown here, I did not show why it's named like this, but it is due to Schrödinger equation. So then it's our Schrödinger equation is written here like as von Neumann equation. And again, von Neumann equation looks as only for these parameters, P1, probability to look up and along x-axis, P2, probability to look along y-axis up, and P3 to look up along z-axis. But because 1 minus P1 minus P2 minus P3 it is up-down, then this equation is sufficient to write down Schrödinger equation and von Neumann equation. And we have the results, and these are parameters which are shown, these are parameters that dequantizer are shown here, and quantizer we found here. It was done recently, it was done in our groups, and I am showing it here. Then finally, I will show the last, which is not necessarily, because recently, the Sudarshan, Linda, Gorynin-Kosakovsky, Sudarshan and Lindblad have written new equation, which is written for environment. And now we show how looks this case. In this case, Gorynin, Sudarshan, Kosakovsky, Lindblad equation. It is look like here. Again, like was looking equation which I have shown. If you introduce 4-dimensional vector with probabilities for qubit, we can find the solution for Sudarshan Lindblad equation, which is shown here, and we can write one solution for this equation if our spin 1/2, it is spin 1/2, moves in magnetic field. If you have spin in magnetic field, this is a solution. This is written solution for evolution of this equation written in probability representation. Now to conclude, we point out that it is clarified, finally clarified, after 1 century. By the way, in 27 is jubileum of quantum mechanics, and we will speak again about after 1 century of discovery of quantum mechanics, with all the known now application of quantum mechanics, it turned out that it's clarified that quantum states can be described by conventional probability distribution, which contain completely the same information, that wave function, initial notion of state in quantum mechanics and density matter. The quantum equation, like Schrödinger equation, von Neumann equation, Gorini-Kosakowski-Sonasham-Blatt equation, can be written in the form of similar kinetic equations, like in classical mechanics or probability distribution describing the quantum system state. Thank you very much. And now I would like to congratulate Viktor Vasilievich Todonov, our chairman, who is governing our conference, and with his 75 jubileum, to which is which we have a fest, namely by this conference. Thank you very much.
Okay, thank you.